It's an honor to be here and give a talk in front of this big audience. Well, introducing myself, I'm saying that I'm just doing applied algebraic geometry. Applied means it can be interpreted in many different ways, but mostly I'm doing computational algebraic geometry, but also combinatorics is also other my side of my research. I'm just happy to introduce my combinatorics side of it. My combinatorics is mostly heavily biased on the algebraic geometry, and then what I want to introduce is I want to talk about tropical geometry and how this can be used in order to understand the classical algebraic geometry. But rather than introducing my results, I will focus on introducing new objects and then concept of the tropical geometry and how they can be used in order to understand the classical algebraic variety. So let me just begin with, my talk will have two parts, which is board and the slides, and I'll begin with a board talk. So first of all, I want to, by the way, this is the joint work with Mei Kai and Josephine. They are both from Georgia Tech. So I want to introduce the tropical algebra first. Tropical algebra is the algebra that can be done over the tropical semi-ring. I wish everyone can read this. We will think about a tropical semi-ring. The base will be given by real field with the union with the infinity, and then we will introduce a tropical summation and tropical multiplication. Sometimes we call this O plus or O multiplication, or sometimes use this tropical summation and tropical multiplication. How we define this? Well, if you add two numbers by the tropical sum, then it is nothing but just taking the minimum of these two numbers. In order to define this minimum, that's why we want to work with over the real. Okay? Likewise, if you do the tropical multiplication of these two numbers, it is nothing but just the regular summation. So tropical sum is nothing but just the minimum, and then tropical multiplication is just the summation. And that's how we define the tropical algebra. Of course, this is not ring, so that's why we call this the tropical semi-ring. I wish this makes sense. And then we will think about K, which is the field with the valuation. A field with the valuation. My favorite field will be complex number. If you think about trivial valuation, everything goes to 0. Or if you know Puget series field, you can also think about this one, whose exponent is given by rational numbers. Or if it is the first time that you heard about Puget series, you can just totally ignore it. You can just work with everything with the complex numbers. So this definition of the tropical summation and multiplication seems weird, but if you understand the valuation, you can understand that this is not just nothing but just arithmetic over the valuation. Okay. So what I want to do is, because I'm an algebraic geometer, I will take objects from the algebraic geometry and I will just tropicalize everything. Let's say that we have f, which is given by a polynomial. Let's say that I will just write down the polynomial. Summation will be given by C alpha, X alpha. Of course, C alpha is the coefficient, X alpha is the exponent. And then let's say that this is the polynomial.
You write X alpha, you mean the single variable? Or
No. It is a polynomial in the several variables. Let me write down that this is a polynomial in x1 or 2. Let's say xn. N is your favorite number, of course. And of course, this will be a function from Cn to just a C because it returns only one variable, or only one number. And of course, you can think about Laurent polynomial if you want. Laurent polynomial means that you want to consider the exponent vector over the integer. You're allowed to have a negative integer, negative exponent, then we'll record this as Laurent polynomial. Of course, if it is the first time that you heard about Laurent polynomial, you can just ignore this. Okay. Now, from this polynomial, I want to define something called tropicalization of this polynomial. Let me just write down this one. W is the new variable because we use the variable x1 up to xn. We want to use a new variable w1 up to wn. What is a tropicalization? This is nothing but I just want to replace everything by tropical sum and tropical multiplication. We have summation, multiplication here. We want to replace everything by tropical thing, which means that if you replace this by tropical summation, then you will have minimum. I wish this makes sense. Of course, alpha will be chosen from z to the n. And then if you take the tropical multiplication for this guy, because we have C alpha, which is coefficient, we should take the valuation of C alpha. And then we have plus sigma of 1 through n for alpha I, W I. Then you just realize that this is obtained by replacing everything by tropical sum and tropical multiplication. I wish this makes sense. And this is called tropicalization. Of single polynomial f. This is how we define this. I wish this makes sense. I just replace everything by tropical sum and tropical multiplication. This is what I do. Any questions? Yes, and then I'm not sure how many of us here are familiar with algebraic geometry, but if you have a variety defined by only one single polynomial, we call that as hypersurface, and then we will define tropical hypersurface. What is this one? This is nothing but collection of W in R to the n, such that I want to make this tropicalization vanish. I want to make this to be a zero. What is the meaning of this vanishing this polynomial? I want to have, let me just write that. Because we want to have a tropicalization, we want to achieve its minimum. What we want to have is the minimum of this tropicalization achieved twice. Collecting this W is called a tropical hypersurface. So if you have a tropicalization of a polynomial, then you have a minimum of several terms in the polynomial. We want to have the minimum, but twice. If you collect those point W over the real, then we record this as a tropical hypersurface. I wish this makes sense.
Do you mean at least twice?
At least twice. At least twice. So third time also it will be contained in the tropical hypersurface as well.
Why does that make sense?
Okay, so
Why?
why this makes
Yeah,
sense?
yeah, yeah.
Why this makes sense? Well, I have two answers. First of all, for silly answer, but probably correct answer is because it makes sense with all the definitions of algebraic geometry. Second, if you have, suppose that you evaluate this polynomial over some point and it is zero, it means that there should be some cancellation between terms. That's why we want to have a minimum contained at least twice. There should be some cancellation happens at some point. That's the kind of the intuition why we want to have a minimum twice. But I think that silly but correct answer is because it works nicely with some algebraic concept.
So I didn't follow this val C alpha. What is that one? C alpha can be complex.
C alpha can be complex coefficient for the polynomial. I mean, we take the valuation, which is a zero in this case. But
So the value
I see,
of
I see,
something,
okay.
what
So
is
they
that?
disappear.
so C alpha is the coefficient. It can be taken from the complex number, or it can be taken from the Puget series, something like that. Whatever the field is, we take the valuation of it. If it is trivial valuation, it's always a zero. If it is like some non-trivial valuation, then it will be some number. Yes, like if you have like Puget series, for example, then your lowest degree will be the valuation.
So in particular, if C alpha is the complex numbers, then nothing here is depending on.
Yeah, right. It will be anyway zero.
Okay.
But so,
What did
but
you say? What did he say?
so if you work over the complex number, then you will have a trivial valuation.
Yes.
Everything goes to zero. That's
You
one.
get just this homogeneous.
Yes. So in general, if you think about Puget series, then you will have some degree of the lowest term. But yeah, as I mentioned, if you don't know about the Puget series, ignore this. Just make that everything to be zero. That's okay for today's talk. So let me give you an example, of course. I wish I can draw the graph of this tropical hypersurface. We have a nice polynomial which is x plus y plus 1, and I want to tropicalize this, and then I want to draw the graph of this. Let me tropicalize this first. If you take the tropicalization, what I'm gonna do is, of course, I would replace everything by tropical sum and tropical multiplication, then you will get minimum of x, y. 1 goes to valuation, it goes to 0, because we take the valuation of this. That's the tropicalization of this polynomial. Of course, if you draw the graph of this, I want to attain the minimum twice. If you attain the minimum x and 0, it means that you have y. If you attain the minimum here and here, then you got x. If you attain the minimum twice here, it means that it should be less than 0, therefore you got to go. This is the graph of the tropical hypersurface given by this polynomial. Of course, I just drew the simple example here, and please try with the cubic polynomial, and then you'll realize that this is really hard to draw. Okay, any questions? This is the tropical hypersurface. And then I'm just finding the tropical counterpart of the order algebraic geometry, objects in the algebraic geometry. So now I will think about an ideal in the polynomial ring. I'm sorry that this is a discrete math seminar, but I'm just doing quite many algebraic geometry here. We have an ideal, and then we will think about variety, which is obtained from this ideal. What I mean by is that I want to collect the zeros or the polynomials inside this ideal. This is called algebraic variety. And then we can define the tropicalization of this one as well. Tropical variety will be defined by intersection of all polynomial in the ideal and its tropicalization. This is how we define the tropical variety. What I mean by is that if you have any set which can be represented in this way, then that is the tropical variety.
Trop VF or just that?
Oh, can you say it again?
Tropical VF or?
Oh, yeah, thanks. Very nice.
This for affine variety, but what about for projective variety?
Projective variety, I think. Yeah, what's the issue that can be happened when you think of regular projective? I'm not
I can see the definition for affine variety. Can you define some similar thing for projective variety?
Yeah, I'm not sure. Maybe it will be just defined in the same way as I understand, but I'm not sure if there's some special way to define the tropical variety. Okay, so I wish this makes sense, and then
I have a quick question.
yes.
So, when we talk about the topicalization of the variety, maybe we fix a certain basis, right?
We fix the first basis. So the question was, do we need to fix the basis for the tropical variety? Yes or no? Because if you look at this definition here, we are taking the intersection for all polynomial inside the ideal. It is infinitely many. But sometimes you can finitely many intersection of this. That is called tropical basis, counterpart of the Grosvenor basis, something like that. Not exactly, but tropical basis. Sometimes you can find finitely many intersections. Okay, so there's one nice theorem, structure theorem. So if you have V, which is an irreducible algebraic variety, d-dimensional variety, what I want to say is tropical variety of its V, it has really nice polyhedral structure. That's what I want to say. Let me just copy down the result. Probably you don't need to worry about too much, but tropical variety of this V is the support of a balanced band. of a pure dimensional that is connected. Through codimensional. I just wrote down a bunch of words in here. Of course, the reason is because you don't need to remember this. What I want to say is, if you have a tropical variety, it has this nice structure. What I want to say is, it has V has a polyhedral structure. So what I want to do today is, I will take the tropicalization of the variety, which is obtained by the rank and most 2 matrix, and then we will understand the polyhedral structure of this. That's what I want to do. But anyway, because it has a nice polyhedral structure, so that's what I want to understand today. Other questions? So, as you can see, I'm talking about rank 2 symmetric matrices here. So I want to think about linear algebra. Let me just define the rank first. I wish everyone knows about the definition of rank here, but let me just write down this again. A matrix A, let me choose a real, has rank R if for its R plus 1 by R plus 1. Yeah, rank n most R, let me say, minor Spanish. I wish you understand the definition of this rank. This is the linear algebra class. And then we already know the notion of this rank. But the reason is because I want to define tropical rank. So let me just write down, first of all, let me just write down minor first. Minor can be written as summation of sigma from Sn, symmetric group, for the sign of sigma, and the product of 1 to n, or xi, sigma. This is the way to write down the determinant. But what I want to talk about is I want to define tropical rank. Tropical rank. We will say that matrix has tropical rank n most R if their tropical minor vanishes. Vanish means that minimum attained twice. We define the tropicalization of the polynomial. We can also define it in this way. If you think about the tropical minor, what is this one? I just replace everything by tropical sum and tropical multiplication. Then you will get this. Or this is the minimum of these terms. So if it attained the minimum twice, then we will say the tropical minor vanishes. Or its tropical minor vanished, then we will say the tropical rank is n most R.
Is tropical rank related to user rank? Like, can you?
So there are question was, is tropical ranks related to the usual rank in the algebraic geometry, in the linear algebra? So if you tropicalize the rank, there are several definitions of rank in the tropical geometry. So this is one of them. There are some Barbinon rank, tropical rank, Cactus rank, some other ranks are there, but this is one of them because this works nicely with our set. So there are several ways to define this. For example, like you can understand like a rank as a summation of the rank 1 matrices. Then that will give you the different rank. I guess that's the Barbinon rank. Yeah, that's I'll just mention. Do I need a password for this? No, I'll just use later. So don't worry. Okay, so this is. Let me give you an example. I always like to work with this easy example. So that let me give identity matrix. Let's think about the rank of this guy. Let's think about the rank of this guy. I will think about 3 by 3 minor of this one. 3 by 3 minor means that we want to take the minimum or the all summation obtained by the symmetric this permutation here. So let me just think about which value that we can get. If you look at this one, this one, this one, then you got 0, and obviously this is the minimum because all entries are non-negative. Likewise, if you choose this one, this one, this one, this is also the one of the terms in the tropical minor, and it also achieves the minimum. Minimum obtained twice, therefore tropical rank is 2. Tropical rank of M is 2 because 3 by 3 minor goes to 0, and then rank is and obviously greater than or equal to 2. Does this make sense? But sorry. But what I want to talk about today is I want to talk about symmetric matrices. Therefore, I want to talk about symmetric matrices. Therefore, I want to define symmetric. I think this is not okay. Symmetric tropical rank. We will say that matrix has a symmetric tropical rank, and most are when all of its tropical minors vanish, including symmetric minors plus symmetric minor. This is the
minor same thing as a principal minor?
Oh, I will talk about this. I will talk about this in a second. So I want to make this tropical minors vanish, but including symmetric minor. I will show what's the meaning of this one. I want to show that symmetric tropical rank of this matrix 3, not 2. Let's look at this matrix here. We got 2 minimum obtained from here and here. However, if you assume the symmetry, symmetry of this matrix, this entry equals to this one because this is x21 equals to x12. Likewise, this entry is same as this one, this entry is the same as this one. Even though, if you assume symmetry of this matrix, even though it looks like it achieved minimum twice, but it only achieved minimum only once. Therefore, symmetric tropical rank of this matrix is not 2, but 3, because its tropical minor does not vanish.
Is there any simpler way to figure out whether this
Given
given some matrix, can you actually calculate whether
whoa,
this is-
that's some hard question. Maybe you can just code or something like that, and then you can just check the one minor one by one.
Okay.
It's a
So it's not clear.
well. That's
Or
why I want to give this talk because I want to give some combinatorial description of this. But in general, if you have a matrix, how can we figure out this? There's no super nice way. You can just
Because for determinant, of course, we know how to do it, but not using this.
yeah, right. How do you assume the symmetry?
Yeah.
Yeah, that's a somehow hard question. And then in general, we just do it. Why?
Okay.
Do you assume that matrix A is symmetric?
So if I give you this matrix, we don't know we assume symmetry or not because. But if you assume symmetry, its symmetric tropical rank is 3.
I mean, when you define symmetric rank, do you?
Oh yeah, we always assume that this matrix. Yeah, thank you guys. Symmetry matrix.
So it's n by n. It's not
N by n. There you go. sorry for many corrections here. I just wanted to. Another example. Let's say that we have a matrix which is n given by 1 0 0 0 0 1 0 1 0. Let's think about this matrix. Let's think about where this minimum attained. We got minimum 0 here. Likewise, we got minimum here. Even though you impose symmetry here, they are all different minors. Therefore, you got minimum twice. You got minimum twice. Therefore, symmetry rank is 2. Symmetry tropical rank is 2. Which this makes sense. So what I want to do today is we have some matrices whose symmetric tropical rank 2. What I want to do is I want to find out the combinatorial representation of them. I want to find that combinatorial representation of them. In order to do this, let me just introduce one more piece of tropical geometry, which is called tropical convexity. Tropical convexity. Let me just write down the definition. Let's say that we have some set, capital S, in R to the n. We will say that this is a tropically convex. This is for tropically convex. Tropically convex. If for any xy in S, and let me say that a, b are just scalar real number, then we want to satisfy the following: a tropical dot plus b times y in capital S. If you satisfy this condition, then we will say that this S is tropically convex.
That's the A and B don't have to be.
We don't have a condition for A and B. So if you look at this one, this is the usual expression for the convexity, ax plus b times y. Of course, in general, you have a and b to be less than 1 or something like that, but we don't assume this condition because we consider valuation. So if you have set something like this, then we will say that this set is tropically convex. And of course, let's say that we have A, which is the set in R to the n. Let's think about set in R to the n. We will think about tropical convex hull, which is the minimum convex, tropically convex and containing this A, which is the, I will define tropical convex hull. Tropical convex hull. This is the smallest set containing, tropically convex set containing. Let me not write down that. Oh, okay, let me write down that. The smallest convex set containing. How we can find out this? It is not easy sometimes. Of course, if you have a bunch of points over the R to the n, then finding a tropical convex hull is not always easy. So characterization of tropical convex hull in some special situation is also a nice problem to work with. But anyway.
Sorry, what is the tropical version in R to the n? Is this coordinate-wise?
Yeah. Of course, like a tropical background, you just consider tropical, coordinate-wise tropical zone and tropical location. Okay, so let me give you one remark here. If you have S, which is tropically convex, then let's think about this. S plus R times 1. This is the scaling of 1, 1, 1, 1, 1 vector. This is the 1, 1, 1, 1, 1 vector, and you just scale them however you want. And then adding this one is still contained in S here. Let's think about this. This is just the observation. What I mean by is that if you have this tropical expression here, adding 1 and 1 here does not change the minimum. Okay? If you achieve minimum here, adding 1, 1 does not change the does not change the fact that this is the minimum. So that if you have a tropically convex set, you can always add the scaling of this 1, 1, 1, 1, 1 vector. Therefore, I'm algebraic geometry, so that I would quotient this out. Like, therefore, usually work with R to the n, scaling this by 1, 1, 1, 1 vector. We call this as tropical projective space. Somehow weird name for this, but you know, projective space.
I'm a bit confused. So what do you mean by adding 1?
And
I
so
mean,
like
if you add 1, you have different set, right?
no, but if you have tropical convex set,
Yes.
adding 1 does not change the convex. It must contain this adding 1 here.
I guess you're taking x equals to y as well.
Yeah. like if you have some tropically convex set, then if you have this point, and point obtained by adding 1, 1 also should be contained there. Because minimum does not change. If you have this set.
So can you draw in the plane a convex set?
Well, we usually draw over the projective space. We always quotient this by 1. So that I will just draw a figure of this later, but this is the graph on this projective space, because otherwise it looks really weird if you do not take this quotient. I will give you an example. So.
Oh, okay, before a quotient, this thing just means I contain all the lines in this direction.
Exactly. Just like really like a fine.
And then you project down here,
and then you have some like a compact.
Yes. So it will be something compact.
Yeah, over this projective space. Yes.
Excuse me, where does the infinity element come?
Infinity.
When you define the summary.
Oh, here.
Yeah.
Where do we have this?
So you say we usually work with RTDN quotient r times this. Yeah, when you define the topical projective space, why should we avoid it? Why there isn't an infinity?
I think infinities work like zero, so we just explain.
Oh, okay. So does that contrast with this definition? Yes. Yeah, I'm not sure which one conflicts with this definition here or there. So we can have infinity because we want to think about the valuation there, but we can still project, I guess. We can just quotient this out by. Of course, 1, 1, 1, 1, 1, which is obtained just like again infinity, which is obtained by 1, 1, 1, 1, 1. Then you just take the quotient out.
I guess that one answer could be this. So only zero coefficient goes to the infinity, the semi-ring. So if you only consider non-zero coefficients, and you don't have to worry about the issue. So I mean,
Okay.
yeah.
So this is introduced in order to make the valuation make sense. Okay, other questions? Yeah, why I want to think about this tropical convexity, because there's some nice results about this tropical convexity by Devlin Santos Stonefells in 2005. Suppose that you have some matrix then tropical rank of M is R. If and only if I will think about the dimension, the tropical convex hull of columns of M is R minus 1. We have this result for the characterization of tropical convex set from this matrix here. So if you have a matrix whose tropical rank equals to M, then if you think about the convex hull of their columns, it must have a dimension R minus 1. So we have a characterization of this. I want to think about rank 2 because it will be a tree. Because it will be a tree. Therefore, let me use this. If you have tropical rank of M equals to 2, then it has tropical convex hull of this matrix is 3. Because each dimension must be just 1. Let me give you a diagram again. Let me give you.
5 dimension.
Yeah, I wonder.
Yeah, like
What's the
locally like dimension locally, something like that.
Is this in the project, like after you project?
After project, yes. I will show you an example. Let's say that we have 5, 0, 0, 0, 3, 0, 0, 0. This is a tropical rank 2. Then what I want to do is, we want to work with a projective space. Therefore, you got 0, negative 5, negative 5, 0, 3, 0, 0, 3, 3. This matrix. If you draw the diagram of this one, then you have, let me just draw this one first. 0, 3, 0. We have x1 direction. We have 0. We have this one, which is length 3. 0, 3, 0. We work over the projective space is corresponding to a point 3, 0 here. Likewise, this point corresponding to 0, 0, 3, so it corresponds to this one. Length is 3, length is 3. So this is the, this is x2 direction. And for this point, I will introduce one more direction because we work over the projective space, which is x0, which is obtained by negative x1, negative x2 somehow. And we have this. This is the tropical convex hull of this matrix. It is true. I wish this makes sense. And then I will put some deco on this. This point corresponding to, let me just label column by 0, 1, 2. 0, 1, 2. This is the 0th column, first column, second column. Let me label them. This is the first column. This is the second column. This is the 0th column. And then using this blue, I will balance this. I will balance this object. Balance this because it comes from this one. In order to make this balance, you can think of a tug of war. 줄다리기. You can check this. Pull this down here to the direction of 1. Pull this down to the direction of 2. Pull this down to the direction of 0. You got 3 decorated by bicolored, so that we call this bicolor tree. This is how you combinatorially characterize your tropical rank 2 matrices. Sorry for messy drawing here. Diligently erase this part.
Oh wait, so maybe you answered before. I didn't understand now what is dimension of the tropical. Why is dimension is 1 is a tree?
Yeah, like that one is a tree.
Why isn't a circle? It's one dimensional. Huh? Topologically, it's one dimensional.
Yeah. Yeah, maybe like a dimension locally dimension is just.
No, a circle. What is the dimension of that circle?
What is the dimension of the circle? It's a 1, I guess.
Yes.
But of
So
course
why
this is
can't
not.
I don't understand.
Yeah. So the
But
question is
Why can't
say
the tropical
dimension
convex
is
hull of
one.
N be a circle? Circle is not a tree,
Circle is not a tree.
but it's
But
dimension 1.
can you get this circle from this tropical convex hull matrix?
That's the
Well,
question.
that I don't know. But you wrote here the rank is R if and only if the dimension of the tropical convex hull of the columns is R minus 1.
Yes.
Yes.
Then can you get
Okay, so
this
this example
object?
is not directly from that statement there. I guess there's some more work.
So initially,
I thought it was.
You put R
I thought the example was a direct consequence
Yeah,
of that equivalence in white.
Yeah.
right. So can you deduce whether it's a tree from this dimension argument?
Oh, no. You only have some specific tree. You need to only have some specific tree that you will correspond
but
to.
that needs. Okay.
So you have to do some more work to deduce.
I mean that's not obvious. I
Yeah.
can see
Okay.
that.
Oh, so I'm sorry. This is the problem.
Yeah, yeah.
This is not okay. How can I fix this? So. Maybe I should put.
I mean, okay, it's not important. I think.
Yeah. This is bicolor tree. So not anything can be obtained in this way, but somehow you have some nice tree which is obtained from this type of construction, then you have a tropical rank 2. That's what I would say. Yeah. So the result was like Hannah Markwick and you in 2009. space of tropical ring to matrices form a simplicial complex of bicolored. This is the result from Markling and Yu in 2009. So if you have such tree, then you have corresponding matrix. If you have tropical rank to matrix, you can also find that the bicolored tree.
So your D and N is fixed, is it?
Oh yeah, the NX is fixed in there. This
Is this Richard true regardless of the elevation?
no, it doesn't matter. Doesn't matter. Well, anyway, you have some valuation something in order to get some tropical matrix anyway, so you don't need to worry about it. But our result is like it is if you have symmetric tropical rank. If you have a tropical rank, then you have bicolored tree. If you have a symmetric tropical rank, then you have symmetric bicolored tree. This is our result. So let me give you an example. Let's say that we have a matrix which is named A0. We have this matrix. A and B are just positive number. Then let me just draw the graph of this guy. It has 0, negative A, 0, 0, B, 0, 0, 0, B, 0. So if you draw this one, then you have this one, and this. Length will be B, and length of this one is A. Now I'll label this. This is 0, 1, 2, so that we have 0, 1, and 2. If you balance this, now you got 1, because you want to get the balance into the direction of 1. And you got 2 here, and you got 0 here. This is symmetric because if you take the symmetry of this around this line, then 2 goes to 2, 1 goes to 1. However, if you take the symmetry about this line, then 2, 2 cannot go to 1, 1 here. This is not symmetric, but this is symmetric. This is a symmetric bicolored tree. Okay.
So the previous example was
It is tropical rank 2, but symmetric tropical rank was 3. It has symmetric tropical rank 2 as well, so that you have a symmetric bicolored. And of course, this formulation will be obtained when you assume that this point is at the origin. You can translate wherever you want. Translate to, like for example, C, D, E. It means that you are adding the matrix 2C, C plus D, C plus E, C, sorry, this is very poor choice of the space, but 2D, D plus E, D plus E, 2B. So what I'm saying is, by translating this point to wherever you want, you can still get this, just a general tropical rank, symmetric tropical rank to matrix as well. If you move this point to the CDE, then it is just like adding this matrix as well. So maybe
Press the little bit button.
little bit, but yeah. So yeah, our result says that the base of symmetric tropical rank 2 matrices form a simplicial fan of structure of symmetrics. Like just like how it is constructed, it can be, you have some parameters there, A, B, and C, D, E there. Just like that, you have some fan structure for this one because they depend on linearly. So this is the diagram of 3x3 symmetric tropical rank 2 matrices. So you have some polyhedral structure like that. And we want to study, there are some other properties of them. First of all, we want to think about some topological property of them, which is called shellability. Shellability is like, you're just like peeling the orange. You want to peeling the orange without breaking it, without breaking its peel. What you want to do is, you have, suppose that you have some polyhedral complex, and you want to peel this one, peel the facets of this without breaking it. If you can do this, then your polyhedral complex is shellable. So what I want to do is I want to peel out the polyhedral orange there. I want to peel without breaking it. And then, well, the result is just like, so this result can be obtained if you define something called shelling order. Let me not talk about this in detail, but if you find out this like a combinatorial ordering, then your simplicial complex is if you find out the shelling order, then your simplicial complex is shellable. And of course, this result is motivated by their result from 2009, and our result says that symmetric tropical rank 2 is also shellable. So this is, after you got this simplicial fan structure, we want to think about some topological property of this. This is one of them. How much time do I have in general? Like
10 minutes.
10 minutes or something. So I want to do some trick here. So that, do we understand it? Everyone here understand what is a matrix or not? Oh.
Can I ask about this result?
Yes.
So this is, you look at all the matrices of fixed size, or the space of all symmetric rank 2 matrices. I don't understand. This could be.
So you have, what can I say? Like you have.
These are symmetric matrices. They could be 2 by 2, they could be 3 by 3, they could be 4 by 4, right?
Yeah, right. So.
And you're looking at the space of all of them.
Exactly. You fix the size, and then you
fix the size.
You fix the size of the matrix, and you consider the set of these matrices. Then they.
And so for each size, you're going to get a fan of a certain dimension.
Yeah,
Is it like this?
exactly.
And what are the dimensions compared to the size?
I don't know.
Okay.
Oh, maybe the dimension would be like, if you have a 3 by 3, then you have 5 parameters there. So dimension, you have 3 parameters there.
Okay.
So the statement is really about symmetric tropical rank 2
Yeah, we.
matrices, n by n matrices.
Yes, exactly. So for the fixed n there. So the next thing is I want to define the matrix out of this. So what I want to do is, can we? Yeah. So let me just do the simple thing here. We have matrix. Suppose that you have a symmetric rank 2 matrices. Then we will think about the parametrization of this one. We have 5 parameters in this one. We have A, B, C, D, E there. So then we can think about corresponding matrix. Corresponding matrix. Sorry. Let me label the row by A, B, C, D, each parameter here. And then let me label the column by their entries. 1, 1, 1, 2, 1, 2, 2. Rows are labeled by parameters. Columns are labeled by their entries. Whenever they appear, we record them. Like, for example, A appears in 0, 0, so that we have 1, 0, 0, 0, 0. Do we have more? Oh, 1, 0, 2C, so then we got 2, 0, 0. 0, 1 is here. We got 0. There's no B here, so this is 0. We got 1, 1, 0. Okay. Likewise, we got 0, 0, 1, 0, 1. And then we got 1, 1, which is here. We have 0, 0, 0, 2, 0. 1, 2 is here, so then we got 0, 1, 0, 1, 1. And the 2, 2 is here, so then we got 0, 0, 0, 0, 2. We got this matrix parameterizing this given symmetry. Then we will define the we will think about the linear matroid of this one. This is the matroid corresponding to the symmetry over the real. Well, I mean they are all anyway integer because they are just integer coefficients. So for example, if you have this symmetry, then you can think about this parameterizing matrix, and from this one you can think about this matrix obtained from these parameters. And we will define a matroid. This is the matroid of the symmetry. So this linear matroid defines the matroid of symmetry. And then if you have a symmetric rank 2, basis of these symmetric trees characterize the basis of regular rank 2 symmetric matrices. So let me simplify that. Like if you have a matrix with the variables, and then you will think about ideal generated by 3 by 3 minors. And then you will think about the algebraic matroid of them. Basis of these matrices, basis of these matroid will be understood by the matroid of these symmetries. This is what we want to do here. And this is actually also the known result by Daniel Bernstein in 2017. He studied this technique for this regular rank 2 matrices. Regular rank 2 matrices. I'm sorry that I cannot introduce the algebraic matrix, but here's the results. So if you have a collection of the bases of the algebraic matrix ranked to symmetry matrix, this is the regular rank to symmetry matrix in usual setting. Rank to symmetry matrices. How can we understand the basis of the algebraic matrix? You will think about only special type of trees, which is called caterpillar symmetries. So this is a caterpillar, and then we will think about caterpillar symmetries. I want to think about the trees with the caterpillar branches. So what I mean by that, this is the trees with the caterpillar branches. If you can characterize the basis of the matroid of these trees, then those are the basis for the rank to symmetry matrices. So in order to understand the algebraic variety, you can only study the specific types of symmetries. This is our result there. Okay. Maybe this is the final slide. Yeah, let me stop here.
Thank you. Any questions?
So in either the 2009 or in your result, what is the major difficulty going to rank 3?
Going to rank 3. What is this guy then? What is the how can you characterize the tropic convex hull, which is the rank 3? Because it is not even a graph.
Yes.
Yes, it is some weird polyhedral polygon in the n-dimensional space. Okay. That's why it's the main difficulty.
Was this user related to the characterization of the Grassmannian tool?
Yes.
Yeah.
Phylogenetic tree? Oh yeah, like phylogenetic trees. I think this is the phylogenetic tree somehow. There's some special type of phylogenetic trees. So I think that Daniel Bernstein in 2017, he was motivated by the study of the phylogenetic tree, tropical geometry interpretation of the phylogenetic trees, and that's how he ended up with the result.
Here, when you say rank to symmetry matrices, you mean the rank to symmetric, the tropical?
No, just the regular, regulars.
Usual.
Yeah. So you define. So you have a matrix with the variables, and then symmetry matrix with the variable. You take the 3 by 3 minors of them. Then you have a rank n most 2 matrices, which is symmetric. And then you define algebraic matrix from them. The basis of these one can be understood by the matrix symmetrics.
By algebraic matroid, you mean?
Algebraic matroid is you take the basis whenever your coordinate projection has a full dimensional, then that's your basis. you have an algebraic variety and you think about the coordinate projection. If it is 4-dimensional, then your coordinates are basis. That's your algebraic matrix. And then from that, how can we find them? And those are the basis for, corresponding to the basis for this matrices.
Any other questions? So if not, let's thank the speaker.